Two, we're going to look at some of the basic operations on matrices. Now, the thing about matrices is because you have those dimensions, you have sometimes things work, sometimes things don't, based on those dimensions. Okay, the positions and the dimension stuff matters as far as rows and columns go. Now, two matrices are considered to be equal as long as they have the same dimensions and all their corresponding parts are equal. Okay, so in order for these two to be equal, what would A21 have to be? 7. That's all this is literally saying. In order for this to be a true statement, then each one of those values, A11 would be the -3, A21 would be the 7, so on and so forth. Okay, I would not expect to see a problem like that on the test.
Please.
No.
Uh-huh.
Matrix addition and scalar multiplication are the two other easy operations we're going to talk about. In order to add two matrices together, they must have the same order. They must have the same dimensions. But when you do it, all you do is add together their corresponding pieces. So if I look at one like A here, well, what's going to be in the upper left of the resulting matrix? Upper right?
-2.
Bottom left?
2.
Bottom right?
3.
And that's honestly all the addition stuff is. You add the corresponding parts. Okay? So then what would be for this C one?
3.
1. And it'd be a 3 by 1 matrix. What about for D? What would be in the upper left for D? Why is it incompatible?
Because there's weird.
Yeah, the dimensions or the order is not the same. This is a 3 by 3. This is a 3 by 2. In order to add them together, they must have the same dimensions. Now, a scalar multiplier just means you have some number out front. All it does is distribute to every value in there. Okay? So, if I have these matrices, and I ask you to find -3a, would that do anything to the dimensions?
No.
No. What's going to be your top row?
-12.
Middle row? Bottom row? -24. 2b, you're just going to double all the values in there. 0.4, or 0.8, -2, 6, and 2, 14. Then what would you do for C? Yeah, but we already actually multiplied them out, right? So just add them together. Matrix addition, order does not matter. It is commutative. Okay? It's associative as well. You can multiply the pieces in it, or add the pieces in any order you need to as well. Associative for scalar multiplication. It doesn't matter if you multiply any constants first or afterwards. You're still going to get the same result. You do have a scalar identity. All it means is if you multiply by 1, it doesn't change anything. Distributive property works both ways. If you're talking about a matrix with a scalar multiplier, with a couple scalar multipliers, or a single scalar multiplier with two different matrices. Distributive property works over addition in both cases. Questions on the addition stuff? Okay. One other thing with addition, you also have, just like you have matrix or scalar multiplier identity, which is just when you multiply by 1, you also have an addition matrix identity. In other words, what would you have to add to every single value to make those values not change? 0. So you actually have something called a zero matrix. Okay, they used to use a capital O for it. It means just add whatever the dimensions on A are, add a bunch of zeros to it. Nothing changes. It's kind of one of those things that's pointless. It feels pointless, but they have to define it that way to make all the different formulas work for it. Okay, so it's more a definition thing. It does not really an issue here. Okay. Yeah, I'm going to skip that one. I'm going to spend some time on the matrix multiplication stuff. For the more challenging part, matrix multiplication. Now, depending on who you had for FS&T, and I honestly don't know how they do it in the plus classes, but matrix multiplication, we're going to have to be able to do it by hand for the quiz. Okay? Now, depending if you jump straight to the calculator, this might be new to you. If you didn't, it's honestly not too bad. If you're fine with section 1, you'll be fine this. It's just organization. This honestly makes it look really convoluted. This is defined in any given position. You multiply the corresponding row from the first matrix times the column from the second matrix. Okay? And then add up those corresponding pieces. The formula to me makes it look worse than it actually is. Okay? But the trick is always just think it's row by column. So first off, does anybody remember the rule if I look for this? How can I tell if I can multiply these or not?
Like the outside ones.
Inside's have to match, and outside is the answer.
Right. Inside ones have to match numbers. So what's the dimensions of this?
3 by 2.
3 by 2. So I have a 3 by 2 times a what? 2 by 2. So because these two match, if these match, then this is your result. So my answer is going to be a 3 by 2 because those two inside ones match. And the trick is, I'm going to pull, because I have 3 rows here, I'm going to pull the rows from here and the columns from here. Okay? So my answer, I'm going to leave myself some room. If I want the first row, first column, I'm going to multiply the first part of that row times the first part of this column. So I have -1 times 1 plus second part of the row times second part of the column, 4 times 0. And you do this for all 6 positions. It's 3 by 2, so you're going to have 6 different numbers in here, right? Top row, second column, what are you going to multiply? -1 times -2 plus 4 times 7. Okay. Now, honestly, I'm not going to expect you to write quite that much. I would just see it makes it easier for you to catch errors if you have them. I would have you write at least at this state what you get. If I want second row, first column, I'm going to do second row, first column. I would have you write the 2 times 1 gives you 2, plus 0 times 0 is 0. Second row, second column over here, be 2 times -2 is -4, plus 0 times 7 is 0. So I kind of have you show at least that much. So then what would you show for the third row, first column?
1 plus 0.
Yeah, 1 plus 0. First row, second column? -2 plus 14. Okay? Does that process make sense? Okay. What is your first column then going to be when you add it all up? Well, I'm sorry. You don't actually add the column. I mean, what are the 3 numbers in the first column going to be? -1. Oh, you were actually saying that now. Okay, I was trying to figure out how you're getting 3. Left center? 2 and 1. Okay.
Sorry.
Now, the column here would be what? In order. What do you got? 30 then? And 12. So that would be your answer, the 2 by 3 matrix. Okay. And honestly, that's the basic process for the matrix multiplication. Even when you have bigger matrices, like this one, how big is the resulting matrix going to be? 3 by 3. So when I do this, what am I going to multiply to get this first upper left position?
4 times 1/4.
4 times the 1/4 plus 0 by 0. 0 by 0. So together I just get what? 1. First row, second column would be what? Be what? 0. So you're multiplying the 4 zeros 0 times the 0, -1/9 and 0. So they just all cancel out. Upper right, 0. Center left, center, center, Yeah, it'd be 1 again. Because 0 and 0, negative 9, and negative 1/9, 0, and the 0 down here. And center right, bottom left.
Bottom right, 1.
Nope. Bottom right is what?
2.5.
2.5. So it's almost a what?
It's almost a RR. Yeah.
It's almost in a reduced row echelon form, but there's actually another name for it when it's a square matrix. If it had all ones on this primary diagonal. Yeah, it's a multiplicative identity matrix. If you multiply any 3x3 matrix or anything with 3 in it times this matrix, like a 3x3 square matrix, then nothing's going to change. It's going to maintain the position of everything, and that's it. Okay? But that one's actually just the matrix. Going down to here. What are the dimensions of my result going to be?
Two by three.
2 by 3. I have a 2 by 2 and a 2 by 3, so it's going to be 2 by 3 on the result. Upper left, 2. You get 0 plus 2. Center,
1.
top right, 0 plus 4, so 4. Okay, bottom left, bottom center,
21 plus 7.
21 plus
2.
2, it'll be 23. Bottom right,
Negative 14 plus 8.
negative 14 plus 8 is
Negative.
negative 6. So that'd be your answer.
We can't see that. Right?
Oops. Well, you guys were saying those anyway. Half your numbers are 0. Okay. For B, what would be your dimensions of the result?
3, 1.
Yeah, it's 3 by 2 and a 2 by 1, so it's going to be
3 by 1.
3 by 1. In other words, it's just going to be a column matrix. What do you get for the top number?
Is that a negative 1 or a 1?
Where are we at?
5.
Yeah, it'd be 6 minus 1. So 5. Center?
12.
Bottom?
3 plus
3 minus 3 is 0. Okay. A couple more like that real fast. What about for C here? What would you get in the top left? Why?
because it's
The middles don't match.
Yeah, the middle numbers don't match. If I tried to multiply this row by this column, I take 0 times 2, 2 times 0, and 4 times, well, nothing that exists. So this one, you can't multiply. What's going to be the size of your resulting matrix for D?
1 by 1.
1 by 1. So it's a 1 by 4 times a 4 by 1. If I flipped it and multiplied it the other way, what would be the dimensions of the answer? 4 by 4. Okay? When I multiply this, what am I going to actually get? Yeah, you got 0 plus 5 minus 6. So, negative 6. And you should actually still keep it inside brackets. Questions so far? Okay. Now, matrix multiplication. Commutative property is off the table. Why?
Because it changes based upon which is first, which is second.
Right. Your order matters. A times B is not the same as B times A when you're talking about matrix multiplication. Scalar multiplication, you're fine. Addition, commutative is fine. Matrix multiplication, it's not. The associative property does still work, though, as long as you do not change the order whatsoever, as far as from left to right goes. So you can multiply BC first or AB first. You're going to get the same result. So do whichever one's easier. Distributive property does work as long as it's a cross addition. Okay? So if A times B plus C, you can distribute the A first. Honestly though, would you really want to do that? No. This is going to be much easier. Because you're only going to have to do matrix multiplication once this way, whereas you have to do it twice this way. Same thing with 3. C, the scalar multiplier, does not distribute over multiplication. It distributes over addition. So don't apply the C to both the A and the B. It's only one or the other. Or just wait until you're done. It's probably going to be the easiest way. All right. We actually already talked about the identity matrix a little bit. Identity matrix is going to be a square matrix always with the primary diagonal being 1 and everything else is zeros. Okay. Couple more things. Consider this linear equation system. I want to write the systems as a matrix equation. Now, a matrix equation means you have A and B are both numeric matrices. X is a variable matrix. Okay? So this A is the coefficient on X. So I'm going to use the coefficients on the X's. So what dimensions will this coefficient matrix be? The A one. Remember, it's only the coefficients. What are my coefficients up there? Right, these aren't coefficients, so it's going to be a 2 by 2. So I have -1, 3, 1, -1. Now, this is a 2 by 2, right? I want to multiply this by the variable matrix. How many components are in the variable matrix?
4.
Careful. 2. You have x1 and x2, and that's it. So then, think about it logically. If I'm going to multiply a times x, am I going to have a 2 by 1 or a 1 by 2 for the variable matrix? 2 by 1. Otherwise, I can't multiply them. So I'm going to do a 2 by 1, which means I'm going to have x1, x2. Now look at this for a second. If I were to multiply this out, I would take -1 times x1 plus 3 times x2. And then I would do the bottom row, 1 times x1 plus -1 times x2. So that gives you the left side of the equal sign. On the right side, you just have the constant matrix, or the solution matrix, which is just going to be 3, 3. So it's just going to show you that relationship. Now, when you did matrices last year, then what you do from there to solve is what? Inverse what? Yeah, inverse of A, yep. And multiply that times.
Solution.
Well, you're actually multiplying times both sides. If you multiply this matrix times its inverse, what are you going to get? The identity. And the identity times x1, x2 just goes away. But, so if you do the inverse of this times this, that's one way you can solve it. Now, what this is asking us to do instead, this just wanted us to write that, and then it says use Gauss-Jordan elimination to solve an augmented version of this matrix. Well, going from this equation, the augmented version allows me just to throw out variables, right? So I can just write it as -1, 3, 3, and 1, -1, 3. Well, if I wanted to use Gauss-Jordan elimination, what would I do?
You can already cross out that negative 1, right?
Do what?
Never mind. Add 1.
What do you want in the upper left?
Just 1.
So what would you do first? I would flip them first. Okay, make sure you try to get that 1 in the upper left first. It's just going to make things easier. Then what? Add row 1 to row 2 and replace row 2. Top row remains the same. Bottom row becomes what? Then what? Divide the second row by 2. In other words, multiply the second row by 1/2. So I'm going to take 1/2 R2 and replace. Top row remains the same. Because it does say Gauss-Jordan, so I'm trying to get this thing to look like what? Yeah, that RREF, right? So then what? Add row 2 to row 1. And replace row 1. Bottom row is going to maintain. Top row is 1, 0, and what? 6. So my solutions are what? 6, 3. Okay. This is just kind of trying to show you the relationship between that AX equals B formula and the augmented matrix stuff. Okay. Questions so far? One more. Gotta have at least one word problem, right? Fruit grower raises 2 crops which are shipped to 3 different outlets. The number of units sent to each outlet is shown below. The profit per unit for the first crop is $3.75. The profit per unit for the second is $7. Okay? I'm going to find the profit for each outlet. Now, would you have to use matrices to do this? Absolutely not. But the truth is, if you're an orchard, do you want to only be shipping to 3 outlets?
No.
Probably not. You're going to be shipping to, hopefully, 50 plus grocery stores around the area where you're at. Or possibly even storing and shipping farther. Right? So this is just really basic version of where you would actually apply this. So I want to turn these into matrices. So I can do one operation and have it spit out an answer for me. So what's the obvious matrix?
Let's give it a table.
Now the table, convert it into a matrix. Okay? Now what are the dimensions on this matrix? 2 by 3. So I have a 2 by 3 matrix where I would just have that 100, 75, 75, 125, 150, and 100. Okay? Now, I want to somehow multiply crop 1's profit times everywhere I have crop 1 up there. 2 values, what are my options?
You just want to get 2 in the end, right?
Hmm?
You just want to get 2 in the end? Or no?
Yeah, basically.
3 by 1? I don't think that.
Okay, I only have 2 things to work from though, right? So either, how could I write this as a matrix? Or
Flip the first
1 by 2.
1 by 2. If it's 1 by 2, I can't put it afterwards, right?
Yeah.
This is 3 by 2. So if I put it here, I'm going to have to make it,
Well, that's 2 by 3. That's 2
or 2 by 3, sorry.
I follow.
So I can't put it here no matter what. I got to put it where?
by 3.
In front, and what do the dimensions have to be? 1 by 2. So, and honestly, that's not the cleanest way to do it. But if you take the table as it is, that's pretty much what you're stuck doing. Okay? My other option with this, if I just throw these values in real quick, is to rewrite this matrix instead of doing 2 by 3, do it as 3 by 2. If I do it as a 3 by 2, I like it this way just because it's more condensed. But you just take your column, or take what was a row and make it a column. Then the matrix I'd multiply it by would be what dimensions?
2 by 1.
2 by 1. And make sure this row is what? So if I put these in,
3.7, yeah.
okay. Problem is these are calculating 2 different things. Or no, actually I take that back. They're calculating the same thing. What am I saying? Sorry. I was thinking the other direction. Okay. Either way, I'm going to get the same results. This way, a 1 by 3. This way, it's going to be 3 by 1. Doesn't actually matter. I just like this way because it's more condensed. Because when I do this, go ahead and punch these into the calculator. Not as matrices, because that would take quite a while. But what would you multiply by to get this top number?
3.75 times
375 plus
100 plus
7 times 125.
Yeah. First times first plus second times second. What do you get? $875 plus $375 is $12.50. Not bad on that one. You're not going to do that on the next one.
Oh, I can't
75 times 375. What do you get for that one, guys? With the calculators. 281.25 plus.
Wait, don't tell me.
I got it.
225. 275 plus
Where are you getting 275?
275 plus
Because it takes,
1,050.
he could just take 3/4 of
275 plus
Guys, with the calculators, what is it?
Take 3/4 of 1250.
Thank you. 1,331.25. It's 31, right? Okay. Lastly, $981.25. So those would be your three. How much profit you're getting from each of the outlets you're shipping to. Questions on this stuff? Okay. The rest of the time is yours.